Okay, we're going to start chapter 7. 7 to begin with is about sequences and series. We're first going to look at what sequences and series are, then we will get into arithmetic sequences and geometric sequences and so forth. The second half of chapter 7 will deal with probability. A sequence is a set of numbers that are the result of a function whose domain is the set of positive integers. In other words, if our domain is 1, 2, 3, 4, 5, the counting numbers, and our function is x squared, then the sequence is 1, 4, 9, 16, and 25. We have a little labeling to help us with our sequence. The first term is called A1, the second term A2, the third term A3, and so forth. If we want the nth term, which would represent a general but undefined term, we call that an. Notice that the subscripts, the numbers are down, and they follow the a, a1, a2, a3, and so forth. It is possible to have a b1, b2, b3 if we were trying to deal with more than one sequence at the same time, but generally we use the A's for a sequence. Now, if we wanted to find the first four terms of a sequence whose general term is given by an equals 2n minus 1, the key is whatever number this n represents, that n has to also represent. So if we wanted to start off with the first term, a1 would equal 2 times 1 minus 1, which is 1. A2 would equal 2 times 2 minus 1, which is 3. A3 would equal 2 times 3 minus 1, which is 5. And so we would start to get 1, 3, 5, and then 2n minus 1 would be some undefined term in the sequence. And so that's how you can find the terms in a sequence based on a general term. There is a second way to do this, which is called basically a recursive formula or a recursive sequence in which each term in the sequence depends on the term before it. For example, in the sequence an equals 2n minus 1, the one we were just looking at, we could rewrite it as an equals an minus 1 plus 2, where whatever term we're talking about, this is the previous term. In other words, if this was A5, that would be A4. If this was A9, that would be A8. And of course, since we are dealing in this particular case with the odd numbers, all our odd numbers are a difference of 2. So if we're at any one odd number, it is the previous odd number plus 2. Let's look at an example of another recursive. Here we have a1 is 4, that's the first term, and our general recursive formula is an equals 5 times an minus 1. So if a1 is 4, then a2 is 5 times a1, which would be 5 times 4, which is 20. A3 would be 5 times A2, which is 5 times 20, which is 100. A4 is 5 times A3, which is 5 times 100, which is 500. So note how in this particular case, each term was 5 times the previous term. Now, you might say, okay, why would we want to do this? It is possible that in some programming applications, in writing code, it might be a lot easier to design it using a recursive formula than it is to use a general term formula. So those are sequences, a series of numbers that are the result of a function or relationship. Now, we also have what's called a series. A series is the sum of a sequence of numbers. In other words, if we have that same sequence of squares that we had before, 1, 4, 9, 16, and 25, and then we simply stick plus signs in between them, we add them up, we get what's called a series. A series has sigma notation that looks like this. This is the symbol sigma, capital letter, for sum in this case. Here, instead of using the n to designate which term we're looking at, we use I as our counter. So this one says I is going from 1 to 5 of I squared. That becomes our function. Again, the capital E looking symbol, it's actually a capital Greek letter. It's for sigma notation. It indicates the terms that are being added together. The I is used for the counter. Usually the starting one goes below, the ending number of the counter goes above, and then it's followed by whatever is the function that we're looking at. So in this case, the sum of I from 1 to 5 of I squared is 1 plus 4 plus 9, the squares, which gets us 255. Here's an example in which we have expanded and simplified something that's written in sigma notation. This is negative 2 to the ith power. That's actually a little typo there, so ignore that part. Just negative 2 to the ith power. And so we're going from 3 to 6. So negative 2 cubed, negative 2 to the 4th, negative 2 to the 5th, negative 2 to the 6th power. And when we actually go ahead and simplify those, we have negative 8 plus 16, negative 32 plus 64. Of course, for negative signs, when we have an odd exponent, it'll still be negative. When we have an even exponent, it'll become positive. And so here we have numbers to add up. We're still adding them. We're just adding negatives and positives together, and we get an answer of 40 there at the end. Now, not too difficult if they give us the sigma notation to just go ahead and expand it and simplify. Little bit trickier if we want to take a sum of numbers that have some kind of pattern to them and figure out what the sigma notation should actually look like. And really the key to figuring out the reverse direction, in other words, here's my set of numbers, what will be the sigma notation when we are done, usually starts with very similar to when we're factoring. In other words, is there a common factor to all of our terms? And in this particular case, 3, 12, 27, and 48 are all divisible by 3. And so if we sort of separate our terms into pieces, we find out that 3 is 3 times 1, 12 is 3 times 4, 27 is 3 times 9, 48 is 3 times 16. We note that basically we have 3 times our squares that we had previously. So a kind of general way of looking at this is a to the I, so the ith term here is 3 times I squared. When basically we had the first term, it was 1 squared, the second term it was 2 squared, the third term it was 3 squared, and so forth. So now that we have that general form, and again we got that by basically factoring out the 3 and then realizing we had squares, we can rewrite it as we're going from 1 to 4 of the formula 3i squared. Now please note, you do not necessarily have to start out at 1. A lot of times they do. You don't have to. But this is the beginning point, and that's the end point. Now, there are some summation properties that sometimes can help us solve problems. If we're doing the summation of some constant number, in other words, we're just adding the same number up over and over again, that simply is n times whatever that constant value was. If we have a constant times some function, so this is ai represents some kind of function, then we can pull that function out side of the summation, do the summation, and then multiply it by that constant. So for instance, in this case here, we could have pulled that 3 out, done the summation of sums squares from 1 to 4, So in other words, it would have been just the 1, 4, 9, and 16. That would have been from 1 to 4. Let's see, so that would have been 10, and that would have been 20. So 10 and 20 is 30. And so there's our sum there. And so it would have been 3 times the 30, which would have been 90. And so if we add the 3, 12, 27, and 48, notice 3 and 27, that's 30. 12 and 48, that's 60. So 30 and 60 gives us 90. 3 times 30 is our 90. So we can just pull it out. Likewise, if we have two different relationships or functions within the summation, we can separate it into two different summations when they are added and subtracted. We have some summation rules that can help us simplify our results sometimes. If all we're doing is adding our counting numbers, so in other words 1 plus 2 plus 3 plus 4 and so forth up to some value, that summation is equal to n times n plus 1 over 2. If we are adding our squares from 1 squared, 2 squared, 3 squared, and so forth, that is n times n plus 1 times 2n plus 1 over 6. And if we are adding our cubes, we'll find out that's 1 cubed, 2 cubed, 3 cubed. That equals n squared times n plus 1 squared over 4. Now, right now, we're just giving you these rules. It turns out that in a later section in the chapter, we'll learn how to actually get those relationships. All right, let us look at some examples now. We're going to take a general form and find out what the first 5 terms of the sequence would be. So here we would have a1, so that's going to equal 1 squared plus 1, which would be 2. a2 would equal 2 squared plus 1, which is 5. a3 would equal 3 squared plus 1, which is 10. a4, 4 squared plus 1, which is 17. And a5, 5 squared plus 1, which equals 26. So our sequence of the first 5 terms here would be 2, 5, 10, 17, and 26. Please note a couple of things here before we move on to the next one. These two have to match. So a1, 1 squared, a2, 2 squared, a3, 3 squared, and so forth. Secondly, I find that it's helpful if whatever your n value is, you put inside parentheses so that you know that's what I'm inputting each time, and then the rest of the formula or pattern I then add on afterwards. That makes it easier for you to keep straight if it turns out you've checked your work, you made a mistake, and then it's like, oh, I see, and you can go back and see perhaps where you've done something wrong. All right, in the second case, we have an equals n plus 1 over n plus 2. So a1 is going to be 1 plus 1 over 1 plus 2, which will be 2/3. a2 is 2 plus 1 over 2 plus 2, which is 3/4. a3 is 3 plus 1 over 3 plus 2, which is 4/5. a4 is 4 plus 1 over 4 plus 2, which is 5 over 6. And a 5 is 5 plus 1 over 5 plus 2, which is 6 over 7. So the sequence for the first 5 terms was 2/3, 3/4, 4/5, 5/6, 6/7. So again, everywhere we have an n, they have to match. So n, 1, 1, 1, 2, 2, 2, 3, 3, 3, and so forth. So a couple of examples in which we have a sequence defined by a general term. Let's now look at a couple of them that are recursive in nature. So here we have a1, and the nth term is the nth minus 1 term, subtract 3. So we have the first one already. We already have a1 is 3. a2 is going to be a1 minus 3. So again, this is one less than that one. So since a1 was 3, we have 3 minus 3, which is 0. a3 is going to be a2 minus 3, which is going to be 0. Subtract 3, which is negative 3. a4 is a3, subtract 3, which is negative 3. Subtract 3 more, negative 6. And a5 is a4, subtract 3, which is negative 6. Subtract 3, which is negative 9. So our first 5 terms are 3, 0, negative 3, negative 6, negative 9. Using a recursive formula. Okay, a second one. Again, they have given us a 1. Now, it is quite possible to have a recursive formula that doesn't have to start at 1. But you do need a beginning place to start, and then you can do all of the terms in the sequence that would go after that first given term. But again, we have a 1. So now we want a2. So following our formula, it's negative 2 times a1. Again, that one has to be 1 less than this one. So 1 less than 2 plus 5. So this is negative 2 times negative 3 plus 5. 2 times 3, that's a 6. It'll be positive. Since we have 2 negatives, 6 and 5 gives us 11. a3 will be negative 2 times a2 plus 5, which will be negative 2 times 11. Again, notice how it's the previous value. And then again, plus 5. So negative 2 times 11, negative 22. Negative 22 and 5 is negative 17. a4 is negative 2 times a3 plus 5. So now I have negative 2 times negative 17 plus 5. So again, 2 negatives positive. 2 times 17 is 34. 34 and 5 is 39. And then a5 will be negative 2 times a4 plus 5 equals negative 2 times 39 plus 5. So 2 times 39 is 78. 78, that's negative 78 plus 5 gives me a negative 73. And so our sequence this time is negative 3, 11, negative 17, 39, and negative 73. So note that all the numbers in a sequence do not have to be positive or negative. They don't have to all be the same sign. It is possible to have them alternate. So a couple of examples in which I have the general term or I have the recursive formula, and I can go ahead then and figure out various terms. Okay, pretty straightforward. Now we're going to go in the opposite direction. We're going to start with some sequences and see if we can figure out what the general form may look like. And when you want to do that, the first thing you want to do is label your terms. So here, that's A1, that's A2, that's A3, and that's A4. And then what you want to do is you need to look for a pattern. A pattern in your numbers will give you a handle on what the general form may look like. The other thing that you want to end up with is you want to end up with something that allows you to count. In other words, we want to use n equals 1, n equals 2, n equals 3, n equals 4 kind of things. So we need to find a 1, 2, 3, 4 type of pattern within our sequence of numbers. So one thing, for example, I look here, I notice that they're all 3 apart. And in fact, I can think of A1 as being 6 plus 1, A2 as being 9 plus 1. In other words, they're all 3 apart, but they're not multiples of 3, but they are all just off of multiples of 3. They're all 1 off of multiples of 3. And so by pulling out that 1, by thinking 6, 9, 12, 15, hey, those are all multiples of 3 and I'm 1 off, then I can go, well, wait a minute, so 6, that's just 3 times 2, and then of course I still have the plus 1, and then 9 is 3 times 3 plus 1, 3 times 4 plus 1, 3 times 5 plus 1. And so what I have managed to do is find those counting numbers. In other words, something that went in order, 2, 3, 4, 5. And so I note that 2, well, that's 1 more than 1. 3, that's 1 more than 2. 4, that's 1 more than 3, and so forth. Therefore, I can generalize this as the AN is 3 times n plus 1. Again, each one of those were 1 more than that one, and then we had that same plus 1. And so I have my general form for problem 5. All right, let's look at problem 6. Again, start off with A1, A2, A3, A4. Now, what I notice here is 2, 4, 8, they're doubling each time. Also, I notice that they're alternating in their signs. Now, if you've done enough of these, you know that when things alternate in their signs, like that other example that I showed you before, if I have a negative number to an exponent, that usually tells me then that when the exponent's odd, I get a negative. When the exponent's even, I get a positive. So that's one of the ways to do that. So that's something that I want to be looking for. Now, let's see. So A1, well, that's negative 2. Now A2, well, that could be 2 times 2, but that's also negative 2 times another negative 2. And why did I pick that? Because that one was a negative 2, and so by doing 2 of them, I'm trying to look for a pattern between them. And then, oh, wait a minute, A3 then would be negative 2 times a negative 2 times a negative 2. 3 negatives, that gives me my 8. And then A4, I'm back to, hey, negative 2 times negative 2, negative 2, and then times negative 2 again. And since I have 4 negative signs, that'll be positive. 2 times 2, that's 4. 4 times 4, that's my 16. So now I found a pattern between them, and I realize, well, hey, this is just negative 2 to the 1 power. This is negative 2 squared. This is negative 2 cubed, and this is negative 2 to the 4th power. And so now there's my numbers, 1, 2, 3, 4, and I can set up a n. The nth term is negative 2 to the n. And so I have my general form. So again, 2 things to mention when I'm doing this. First off, label A1, A2, A3, A4. Secondly, try to break our numbers down so eventually I can see something that goes in order. Here 2, 3, 4, 5, here 1, 2, 3, 4, because I need a relationship between those numbers and the subscripts. When they match, it's just the same. In this case, they all ended up being 1 above, so I needed to use n plus 1 instead of just n. All right, let's look at some summation notation, expand and simplify. So in this particular case, again, I is going to start out at 1 and go up to 5. So everywhere I have an I, I'm going to put in 1, then 2, then 3, then 4, then 5. So first off, we're going to have 3 times 1 minus 1 plus 3 times 2 minus 1 plus 3 times 3 minus 1 plus 3 times 4, subtract 1, plus 3 times 5, subtract 1. So that is what is meant by expand. Alright, now let's simplify. So here I have 3 minus 1, that's 2. Here I have 6 minus 1, that's 5. 9 minus 1, that's 8. 12 minus 1, that's 11. And 15 minus 1, that's 14. So in this particular case, adding these up, 7, 15, 30, let's see, 26, and 14 is 40. All right, in this one, I have I is going from 2 to 6. So we've got 2 times 2 squared plus 1 plus 2 times 3 squared plus 1 plus 2 times 4 squared plus 1 plus 2 times 5 squared plus 1 plus 2 times 6 squared plus 1. So there is the expansion. Okay, so 2 times 4, 8, 1 is 9. 2 times 9 plus 1 is 19. 2 times 16, 32 plus 1 is 33. 2 times 25 plus 1, 50 and 1 is 51. 2 times 36, 72 plus 1, 73. Which equals 185. Now I might mention that we could have separated this into 2 times I equals 2 to the 6th of I squared plus I equals 2 to the 6th of 1. So we split that, we put the 2 out front, split it into 2 parts. Now, this part will be 2 times, okay, well we're doing the squares from 2 up to 6, so that's 4 plus 9 plus 16 plus 25 plus 36. And here, since I'm going from 2 to 6, that's 2, 3, 4, 5, 6. That's 5 of them. 5 times 1 will be just plus 5. And adding all of those up, I'm going to get 90. 90 times 2 is 180. 180 plus 5, and we get our 185. Okay, here the counter is in the exponent. So we're going to have, first off, negative 2 to the negative 1 plus negative 2 to the negative 2 plus negative 2 to the negative 3 plus negative 2 to the negative 4. Just because the way this one was written, I didn't put the i's inside parentheses, but they're separated from the rest of it, so it's easy to tell. Here's my 1, 2, 3, and 4. Now remember, negative exponents mean 1 over, so in fact this is just going to be negative 1/2, and then a positive 1/4, a negative 1/8, and a positive 1/16. Now, the positives and negatives are not because of the exponents, they are because I took negative 2 here, so that gave me negative. Negative 2 squared turns to positive. Negative 2 cubed turns to negative. So really, this was 1 over negative 2, 1 over positive 4, 1 over negative 8, and 1 over positive 16. Now, of course, when I'm adding fractions, I have to have common denominators, and so this would be 8 over 16, 4 over 16, 2 over 16, and then 1 over 16. And so my final answer is 5 over 16. Okay, going from 1 to 5 of x plus I. Now again, it's the I that's going to change from 1 to 5, not the x. Doesn't matter, we still follow the same process that we had before. So we're going to have x plus 1, x plus 2, x plus 3, x plus 4, and x plus 5. So 1, 2, 3, 4, 5 will give me 5x. 1 plus 2 plus 3 plus 4 plus 5 is 15. So no, I do not have to end up with an actual value at the end. I can have a function instead. Now, don't forget, we could have split this up. So I equals 1 to 5 of x plus I would have been the sum of I equals 1 to 5 of x plus the sum of I equals 1 to 5 of I, which this part here, since that's not part of the I, that's just like a constant in this case, would have been 5x. Now the other part, using that summation formula, n times n plus 1 over 2, well, we're going n as 5 here, so it would have been 5 times 5 plus 1 over 2, which is 5 times 6 over 2, which is 15, and so we're back to our answer. Okay, last two examples. We're going to go from our sequence of numbers, which are sums. So we want to end up with summation notation for these. Now the problem is that, this is probably one of the hardest things that, we've done all year, because, it's not just a matter of using some formula. We've got to come up with the formula. We have to look for a pattern. So the first thing is I'm going to label my different terms. I notice that all of these are odd numbers, so that's helpful. However, I started at 3, so I need to figure out some way to basically get a 1, 2, 3, 4, 5 in my sequence of numbers. So let's see. A1, well, that's 2 plus 1. A2, that's 4 plus 1. A3, that's 6 plus 1. A4, that's 8 plus 1. And A5, that's 10 plus 1. Now you might say, well, how does that help? I'm just taking the even numbers plus 1. Yes, I am. But now note that instead of dealing with the 3, 5, 7, and 9, what I'm dealing with is 2, 4, 6, 8, 10. And in each case, that number is twice what the subscript number is. In other words, basically, this is 2 times 1 plus 1. This is 2 times 2 plus 1. This is 2 times 3 plus 1. This is 2 times 4 plus 1. And this is 2 times 5 plus 1. And so there's my 1, 2, 3, 4, 5 to match my 1, 2, 3, 4, 5. That's really the trick, if you will. Find the set of numbers that will match my subscripts, and that will allow me then to write it in a general form. And so my summation notation is I is going from 1 to 5, and it's basically 2 times I plus 1. And so there is my general form. Now in the second one, again, we're going to start off A1, A2, A3, A4, A5. The thing to note here is I have alternating signs. And one of the ways to take care of alternating signs is I need my counter to be in the exponent. And so I need to look for my 1, 2, 3 within the exponent to help me there. The other thing to note is it starts off with a positive and the second one's negative. So my exponents are going to be slightly off because remember, odd exponents give me negative numbers. Even exponents give me positive numbers. So the fact that I know it's alternating tells me it's going to go from odd to even, but the second term here is odd. So it's the even terms that are odd. So I'm going to have some little way of adjusting it so that I have my exponents come out right. Now, the other thing I notice is these again are all multiples of 3. So let's factor out a 3 from our different problems. So A1, well, that's 3 times 1. A2, well, that's 3 times negative 2. A3, that's 3 times 4. A4, that's 3 times negative 8. And A5, that's 3 times 16. So I factored out a 3, and then I notice I have 2, 4, 8, 16. So I'm doubling each time. In other words, I have another times 2. But the thing is, you know, here I have negative 2. So negative 2 times negative 2 would give me a positive 4. And 4 times negative 2 would give me a negative 8. And negative 2 times negative 2 would give me a positive 16. But there's only 1 here, and here I have 2. So I have to figure out a way of doing that. And then it's like, okay, well, what about this one? You know, how do I get around that? Well, if we think in terms of this is 3 times negative 2 to the 1 power, and then this one is 3 times negative 2 to the 2 power, so negative 2 times negative 2, and then 3 times negative 2 cubed, and then 3 times negative 2 to the 4th power. All right, so what about this one? Well, don't forget, anything to the 0 power is a 1. So, 1, 2, 3, 4, but we started at 0. Here I have 1, 2, 3, 4, 5. These are all one more than those, or another way of looking at it, these exponents are all one less than my counting number here. So I can summarize this of I is going from 1 to 5 again. We have our 3, we have our negative 2, but what's about the exponent? Well, the exponent is I minus 1. 1 minus 1 gives me my 0 for the first term. Go up by 1. 2 minus 1 gives me my 1 for the second term. 3 minus 1 gives me my 2 for the third term, and so forth. And so I have found a general form for this series. And again, I started first with A1, A2, A3, A4, A5, factored out a common factor, looked at what I had remaining, recognized that these are doubling each time, but the charge or the sign is changing each time. So therefore, negative 2, 1, negative 2 squared, negative 2 cubed, and then recognizing that these are all 1 less than those. And so there is my general form. And so a quick look at sequences and series.